Okay, hello everyone. Happy New Year. Thank you very much for coming to the first seminar of 2024. This year we're starting earlier, so today. It is my pleasure to introduce Andreas, who is visiting Costa actually. He did his PhD in Queen Mary, then in Imperial, sorry. Then went to Warsaw for a postdoc, and now is a postdoc at the University of Porto. So without further ado, we're all yours.
Hi, thanks very much for having me, for the hospitality. I'm starting the academic year in strength, so thanks for bearing with me. So I'm going to present some of the relatively recent work we did with my collaborators in Warsaw, and also yours truly, Giorgio here and Matteo from upstairs. So we were looking at uh, studying phase transitions after inflation as a means to generate gravitational waves. And get the signatures to kind of reverse engineer and map into your early universe. Now I said a lot of technical words, so that we're gonna cover them, and I'll try to be very gentle, but please stop me if I say something that goes over your head or anything. And George also please interrupt me if I say something that is wrong. So now I've been doing early universe cosmology for a long time. So I think here I will be going very slow, but that will probably be a big mistake. So again, please bear with me and tell me, okay, this is not trivial, right? So I'm using this very nice picture from Guillaume Domenech about the early universe. We don't have to worry about all of the details. It's just a nice picture to show the cosmological picture. We're dealing with early universe. And what do we mean by that? We mean this kind of ambiguous time period where you have inflation, presumably, reheating, presumably, everything that is before your standard hot Big Bang scenario. So before radiation domination and matter domination, and of course the large scale structure of the end, right? So the kind of the blue unexplored part that Ian is showing here. So this is kind of the tutorial overview of what is going on. So you are starting from something unknown here. You don't know what. You are stretching very very quickly to this exponential expansion that we call it inflation. Then at some point you are kind of generating the standard model particles in the process called as reheating. All of these are not very well understood. Then you have your decouple the neutrinos decouple at some place, at some point, then you're seeing big photons, and you end up with your kind of late universe picture at the very end. And now when we're talking about inflation, which is kind of the main theme in this talk, is there are other theories as well for the early universe. This is kind of the most prominent mechanism to explain, and its very big success is in providing, besides the usual cosmological problems that they were trying to solve in the 80s, the kind of more modern and more relevant one is it gives you the mechanism to start from kind of the initial quantum state where you have various quantum fluctuations, exponentially expand and then stretch them so they fall outside of your horizon. And when they re-enter your horizon, they can give you the seeds for your gravity now to kick in and give you the large scale structure at the late universe. This is kind of the idea. This is why people like it so much. And now when we're talking about gravitational waves, which I'm gonna come back at the very end of the talk, but it's just nice to have in mind what we are looking at. So the idea for gravitational waves when they are produced in the early universe is that they propagate unhindered. They do not interact only gravitationally, right? So whatever message you have here in the early universe that is captured by the gravitational waves, it doesn't see any of those. So you get all of the information that is encoded here. That this is why people are looking in primordial gravitational waves. This is the advantage. For inflation, again, I'm just quoting like the standard textbook stuff. There are the supporting evidence from CNBI isotropies where you see the isotropies during the temperature. But now moving, yes.
What do you mean with explored and unexplored there in the
So this is from Guillaume's article, from his point of view. So, but is largely what is been going on in the literature. So, standard Big Bang and kind of late universe cosmology has been explored, kind of understood well enough of course, not, there are open problems. This period of inflation, which is the usual de Sitter slow roll, which is kind of the simple approximations, also has been very much explored, many models, and things work out. Before, we don't really know what is going on, modified gravities or some quantum gravity theories, whatever. And afterwards, so going between like the kind of simple inflationary picture to radiation domination. So how do you get from this to standard model here is not trivial. There are models, there are people are looking into it, but it's not very well understood. I think this is what Guillaume is mentioning here. There are a lot of propositions, but it's not as established as, for example, inflation on its own. It really depends on your model, your gravity. Like it is a mess. Okay, and it's where we are also now putting like this work is fit in this window. Okay, so very primary crash course on inflation, just that we are all on the same page. So typically, when you're talking about inflation, you have a scalar field called the inflaton, the original name, which has this characteristic equation of motion. So this is a typical equation of motion that you have for a Klein-Gordon with the addition of this additional term. So this comes with this Hubble rate as well, which is the dragging from the expansion of the universe. It's exponential and it's actually significant. And everything always comes in terms of the potential of the inflaton. So whatever inflationary model you have, you plug in your potential here and you do your things. Of course, this is not any potential. It has to have certain characteristics. So when you're talking about now perfect fluids, you have your inflaton now that's characterized by this energy density and the pressure of the universe, right? So the energy density, kinetic term plus the potential. This is from the stress energy tensor, and the pressure kinetic minus the potential. And now, very famously in cosmology, you have your Friedmann equation to characterize the expansion of the universe. So Hubble rate, which is the time derivative of the scale factor of your metric over your scale factor, which is given in terms of whatever you have at the energy density. Now that we're talking about inflation, it's going to be this, but if you have additional sectors there, you add them. This is a completely generic equation. And now here I'm just mentioning this just so that you know when I use it again, but you don't have to worry about this. Is just a change of variables. So if holdings of inflation is this capital N, this is just the change of variables between the scale factor. Because these are big numbers, you have exponential expansion. So for the numerics and for all of the discussion, this is not really relevant to talk in terms of them. So we're taking the logarithm to talk in terms of if holdings. So for example, if you want to make sense of the observations, you need typically 60 if holdings of inflation. That means that your scale factor has grown by a factor of 8 to the 60, e to the 60. So this is the idea. Anyway, you don't have to worry about it. This is a kind of a time variable. And now these are the conditions that I mentioned up. So you have this slow roll de Sitter phase, the well understood inflationary phase, where your potential should be approximately constant. So it's very slowly varies with your field, approximately flat. So your inflaton is not doing any rapid movements in the sense to give you this approximately constant exponential expansion. I'm going to show you the potentials afterwards. But when you do this, your Friedmann equation and your equation of motion, they get these very simple forms, and then you can play with them much more easily than having to do with the second order here in the full Friedmann with both terms. These are very generic inflationary cosmology quantities. And you don't have to worry. Yes.
And the inflaton field is a real scalar.
Real scalar, yes. But you can have, now you open Pandora's box. You can have inflationary cosmologists now can play with everything. So everything I'm going to say has to do with a single real field, but whatever you want to have, you can have. And typically you add degrees of freedom and you can do basically everything. This is the problem. Like we have too many models. Okay, so I think this is a very nice picture from Javi's review about quintessential inflation. I'm going to mention briefly quintessential inflation, but it's not absolutely necessary for most of the discussion here. So everything I'm going to, well, most of what I'm going to say is going to be quite generic. And whenever the quintessential inflation comes into effect, I will stress that point. So what do you have when you have inflation in general? This is this approximately constant plateau in your potential. So here you have exponential expansion. So this is the early universe. Then at some point, inflation has to finish. So you go into this kind of minimum. You have this period of kination, where now it's not that the potential is dominating your energy density, but it's the kinetic energy. And this is generic in all inflationary models. Then you enter the period of hot Big Bang, so radiation domination and matter domination. And then at the late universe, you have dark energy. So again, you have approximately constant phase there. And when you're doing quintessential inflation, essentially you want to use one potential to explain both. So that's why you start here and then you have this runaway plateau at the late universe. So quintessential means that you're doing both expansion in the early universe and quintessence of that energy in the late universe. And these periods are all, again, generic in all of the inflationary models, but when you have quintessential inflation, you have a more extended period of kination because there's nothing slowing down the field. When you have the kind of generic inflationary models, when now this potential will turn around, right? You have like a global minimum here. The usual picture there is that your inflaton fast rolls here, and then it oscillates around. You're coupled to standard model fields, you reheat, and this is like the typical picture. In quintessential inflation, you just roll down, then you produce some radiation, it takes over, and then at the very late universe, you dominate again. You don't have to worry about it too much. This is just kind of the idea to have in mind. And this is the same picture, now to have it in a more useful way for us. So same evolution, but now looking at it through the equation of phase parameter, which is this W. It just relates the pressure of the universe with the energy density. So pressure is given by this, energy density is given by this, stress energy tensor, all of these are generic, right? So what's happening? So now when you plug this in, during inflation, your potential is the one that's dominating. So this over this is -1, right? Same in the late universe. During kination, the other way is the other way around. So you have +1. So your equation of phase parameter jumps from -1 +1. In radiation, very famously, you have 1/3 for your pressure for your state. Then you have pressure versus matter, so 0, and then you go. So this kind of the evolution. And we are really interested in the transition between inflation and kination because exactly of this kind of cosmic clock that we treat here. This is the time derivative. And here I've written everything in terms of these e-folds of inflation, just that we can get used to seeing them. Okay. So this is where we start with a more specific stuff. All of these are completely generic, but now we're going to jump into what the mechanism is about. So you have the Ricci scalar that characterizes space-time curvature, right? This is the expression that it has in the early universe when you write it. Well, there when you write it in terms of the equation of state parameter, right? So depending on the value of this, again, completely model independent. Whatever you put there, you can compute from here. And here we saw you the evolution of the Ricci, the Hubble rate, and the equation of state. So we parameterize the equation of state with a hyperbolic tangent because it goes between -1 and 1. Again, completely model independent. Whatever model you want, then you can just quantify from the parameters you use. So this is from the same from the previous slide, right? From -1 to 1. Your Hubble rate drops, so it's approximately constant. There is one during inflation, and it drops a little bit as you go along. And then for your Ricci scalar, the space-time curvature, this is where the significance comes. This is the heart of the calculation. The Ricci scalar during inflation is approximately constant, and then towards the end of inflation, it becomes negative. Then, depending on what exactly inflationary model you have, it can oscillate around, like the oscillating scalar field from before, or in quintessential inflation, it just tend asymptotically to zero. So this is what is gonna induce the phase transition and generate the gravitational waves in our scenario. This is where it comes from. Here I have two comments about why using this quintessential inflation in the first place. Although again, most of the things that I'm gonna say are completely generic, but if you remain within quintessential inflation, so this asymptotically tending behavior, you don't have oscillations, so you only have to worry about one phase transition, which I'm gonna cover later on. And this kind of long period of kination will amplify your gravitational wave signal, so it's going to be better for your detector sensitivity. So this is the idea. Okay. So now, talking about the phase transition, there's also, we shouldn't worry too much about it. It's having the general picture. So you're writing down a theory, your particle theory now. And what did we do here? So in this master action, we include everything we want. Of course, there is standard model behind, but we don't include them because it's going to be a mess. So what do you have? You have this term, so this Planck mass times the Ricci scalar, which is your Einstein-Hilbert term. So this is general relativity, nothing more fancy. You have the Lagrangian of the inflaton that does inflation. We don't specify, whatever it does its thing, it works. We don't worry about it. Then you have this additional spectator scalar field that we add, this guy, so beyond standard model, whatever. So kinetic term, canonical kinetic term, a potential, whatever you want. And then this is very important. You have a coupling between the field and the space-time curvature, non-minimal coupling psi, which is very typical of when you're looking at the early universe. In the early universe, whatever fields you have, you always have to include coupling terms between the field and space-time curvature, because you need it for the renormalizability of the theory. And even if you set it zero at some scale, because these couplings are running, they will have a non-zero value, so you cannot never, well, at a different scale, so you can never really avoid that. So it's not something that you really adding by hand. It has to be there at the moment you are adding this additional field, right? Okay, so now the idea is that we want inflation to work as it does, ZR to work as it does, and now this field, we want to make it so that it does a very strong phase transition, that it produces strong gravitational waves, that we look at them and then say, aha, this is the model, this is the mechanism. We see that in the early universe, whatever. So we chose this very nice potential. So whenever I'm going to show things in this green, it's going to be the model dependent things that we put. Everything else is model independent. So you plug this in, is a renormalizable potential. So quadratic term, cubic term, quartic term. The minus sign here allows you to have the very nice double well potential that you need for phase transitions, as I'm going to show you. And now what is going on is that this on its own can have the double well that will give you phase transitions, but we want to induce it from the curvature. Yes.
Why you don't push it? That copy.
So you can have, it doesn't have a direct Z2 symmetry. You can have it. It will not change the energy release from the phase transition. It will only change the position of the minima. So for this calculation, it wouldn't make any difference. But in principle, you can have it, of course. Yes. You can have Higgs portal as well. You can have whatever you want. Okay, so you have this double well potential. And now we want to induce the phase transition from curvature, from the evolution of curvature. And that happens because you have the non-minimal term. This is time dependent. So now your effective mass, now you have your quadratic term, and now you have this psi r that is time dependent. All of this decreases with time due to the evolution of this, and your potential barrier will decrease. So it will increase the possibility of having the phase transition. What am I talking about? Double well potentials. So you have your false vacuum here. This is the state that you're currently in. You have a tall potential barrier between them, and then you have a true vacuum position at a higher field value. So you're here, and now if by some way you find yourself here, you have a phase transition. Now, the way that this can happen is either a first order or a second order. The first order is the violent one that produces the gravitational wave. The second order is kind of the runaway process that doesn't give you anything. So what do you have here? So tall barrier at the kind of early times, so before nucleation, before bubble nucleation, which I'm going to cover later on. At some point, the barrier comes down and down and down, and you have this kind of critical barrier that now it's probable to tunnel from this position down here. And at that point, you have phase transition. At that point, you nucleate a bubble of this new phase at some point in space-time, and that grows. So all of your universe has this phase for this scalar field, and at some point in your universe, you have this phase. And these bubbles happen at different points in the universe, and they grow, they collide, and then the whole universe fills with this new phase. And then that's when the phase transition completes. This is the mechanism. If, for example, this wouldn't happen, and then your barrier would go down slowly, then you would have this second order phase transition, where you don't have a barrier, and all of your universe finds its way naturally to this. Okay. So these are the kind of the technical details. Again, we don't have to worry about them too much. It's just to be there so that to show you what is going on in the calculation. So the potential barrier decreases between the two phases, right? You have the phase transition via quantum tunneling, and you nucleate bubbles at these positions. So you can quantify this by having this nucleation rate, which is given by this expression. So you have the vacuum excitation value of your scalar field, which is given by this in this model, right? The green one is now in the model that I specified, and you have this Euclidean action that has to do with the instanton calculation for these double well potentials. These are kind of textbook calculations when you have phase transitions, and then you have this kind of analytic approximation for the Euclidean action. So everything is given in terms of this delta, which is now the only meaningful parameter. You have some numerical factors here, and your couplings coming into the game. So now this delta, this encodes all of your couplings and your time dependence there. And the interesting range for the values is between 0 and 2. So 0 corresponds to vanishing barrier when it completely goes away, and 2 corresponds to when the two vacua are completely the same. So it's equal probability to go back and forth, right? So in between, somewhere there in between, you have a kind of this critical barrier that is probable enough that you can tunnel through. This is the idea.
Sorry, probably a silly question, but why is it called bubbles, and why people talk about them colliding? Where does the word come from?
So because there is spherical symmetry, so this transition happens at a specific point, let's say here, and it grows with a spherical symmetry because it's the most economical way for it to grow. It would need more energy to grow in like a rectangular shape, right? It happens here. But because this is quantum tunneling, the probability of it to happen at a specific point is not the same as the next point. So there is some slight delays between points in the universe. So it happens one here, one next door, whatever. They grow in spherically symmetric way. At some point they collide. Then there is some non-trivial physics going on there. But once all of them collide and they settle, you have now this new phase, and you don't have any bubbles anymore. So I have one picture at the end. Well, maybe I can show it now because it probably serves the purpose. One moment. Here. So false vacuum is the purple around. So this is kind of the universe before the phase transition. At some points in the universe, you have true vacuum. It happened there. They grow, they grow, they grow, they grow. They collide, they percolate. Now inside here, you have this kind of true vacuum universe, and then the next box would be all of it would be black. Right? Here you have the gravitational waves from the collisions. This is the idea. It's, I think, similar in fluid mechanics. When you have phase transitions between like the liquids and stuff, you can have similar mechanics, I think. Well,
Probably.
Can I stop for a question? Can I ask another question?
Yeah.
Exactly in the slide you were showing, the one with the bubble. Those regions in between, I mean, those are topological defects.
yes.
Yeah, but if you have coupling with curvature, the topological defects, they will follow the fixed in the curvature. Did you consider that effect?
We don't consider it. There are approximations there, has to do with how thick the walls are and what approximation you are using. We're going the most simple way possible, just to see if the mechanism works, because this curvature-induced mechanism is new. So this was all of our focus. But worrying about this and worrying about if there is plasma, in our case there's not, because it's in early universe before the plasma is there. But if there is also plasma and the interaction with that, this is very hot research happening right now, and very good groups are disagreeing on what is going on there. Their numerics are very hard. There are it's very very interesting and very complicated. You have to be very careful about what is going on there.
Yeah, I do have simulations.
So
I do have simulations for this effect.
okay,
Which is okay.
sure, yeah. I have never done the simulation, so I wouldn't behave as if I knew. But this is what I from Marek in Warsaw, who is an expert in that, and I hear them and they disagree with the other group in Germany or whatever. So not fighting, but disagreeing on some results. But it's very hard. Like when I talk with them, the things that you have to consider are a lot. Well. Okay. Are there more questions? Should I? Okay. I continue and interact with there's more. Um, so when you are using the model that I showed you before, now this kind of delta, your master variable that controls everything, is just given in terms of your couplings, right, and your space-time curvature. So this encodes all of the evolution. And now this is kind of the terminology to use when you're doing phase transition. So now your potential, you can write it in this very nice simple form. So the only free parameter here, right, is the delta, that's where it comes from. And you plug your everything in Mathematica, and you calculate your potential, and it looks very, very good. Okay. So we're talking about bubble nucleation and everything. So what is going on? So you have a nucleation rate, and the easy assumption is to assume that you have one bubble per horizon at approximately constant Hubble rate. So this is the nucleation condition that has to be satisfied in order to have sufficient bubble production. So for some parameters, your nucleation rate, so this is early times, these are later times. So your delta starts from large values to smaller values. So your nucleation rate increases. At some point, it crosses 1. So you have a bubble forming here, and all of the time here, it can still give bubbles, right? And depending on your couplings, this can happen at a different place. So this shows kind of the numerical simulation that the guys computed. I think Mateus and Maciek, Giorgio, and Matteo. And you in the lines, you also see the analytic, semi-analytic approximation. Anyway, so this is kind of your last ingredient to put in to do the calculation. And here there is kind of model-independent moment. If you want to fulfill the nucleation condition and everything to behave correctly, you have some weird, almost analytic function for your delta that it needs to obey, which this delta now corresponds to couplings, right? So everything matches on its own. You get roughly some idea of where the couplings should be, roughly. This is like this. Take it very, very graciously. It's not a hard bound, but this is kind of you see how to make your model be a bit constrained. Otherwise, the parameter space is too large. Like you don't end up everything. You have to scan over all possibilities.
So what is the gamma in this group?
The gamma is the nucleation rate. It's this. Sorry. How probable it is to have a bubble form within one horizon.
Okay, one horizon.
And this depends on the potential, essentially. So it's not shown here, but it's a function of coupling lambda and of delta, and delta is all of the couplings. It has to do with your potential. So how probable it is?
And you're assuming it close to 1.
Sorry?
You're assuming it is close to 1. Because bubble is the rapid correction.
Yes. So here they fix it because this is the trivial.
So you fix it.
Yeah.
So may I ask how many free parameters do you have?
So the model has 1, 2, 3, 4 for the BSM model. And then there is a matter of how fast you are going from inflation to kination. So there's the particle physics model that has 4 free parameters, and then there is your kind of cosmology, your inflation that has 1 free parameter in this scenario. So I showed here, for example. So everything is quantified how quickly this beta, how quickly you go from -1 from inflation to kination. So this is the 5th free parameter.
So this parameter is has nothing to do with the equation.
Yes, yes. And we just don't mess with it too much. We assume that it behaves, you put what you want to have, and because these things don't talk to each other, there's no reason why they should affect each other.
So when you say that the phase transition from the potential barrier happens like quantum tunneling,
Yeah.
is that just the name, or are you actually quantizing it?
We're not quantizing. We're just calculating. Like there is this semi-classical approximation from Sidney Coleman in these papers in the 70s, 80s. So you do like some analytic continuation from imaginary time, whatever, and then you're calculating the bounces, something like that. Is not quantum, it's not classical, it's semi-classical. But you're not quantizing the field. It is a quantum effect, but you're not quantizing the field.
So you're assuming some quantum property
Yep.
in the field without fully quantizing.
Yes, yes. So it's not rigorous, but it's the best you can do. Yeah. Okay. Okay. So now we don't have to worry about the technical stuff anymore. Just to show you illustrative, what are the things that go into the calculations of gravitational waves. So one very important parameter that you're going to hear in all of these talks are the strength of the phase transition, this alpha. So the stronger the phase transition, the stronger the gravitational wave signal. So you want them to be as strong as possible. And what is the strength? Is just the energy released from the phase transition compared to the background energy. So the background at this point is that what energy is left over during kination, which is just the scale of inflation, where inflation has finished, right? And the energy release is just the difference between the two phases, right? The true and the false vacuum. And very nicely in this model, you get something that is you approximate analytically, and it's a function of your cubic and your quartic calculus, right? So what you see here is just this scan that the guys did. So sigma versus lambda, and you see you want to have as high alphas as possible to have the strong phase transitions. So your sigma, you see you have always to go as large as possible and as small as possible for lambda. Just get a sense of what is going on. And there is some comments, I think, about the range between the strength of the transition. So you go below this, you're going into second order phase transition, so not really gravitational waves anymore. Above this, you mess up with your field not being subdominant anymore and affecting the cosmological back reactions and stuff. So you're limiting yourself between these kind of values. This is the idea. Of course, you can consider higher values, I think, when you're doing conformal theories, but we're not doing this here. Okay.
Can I ask one question?
Yeah.
It's very trivial, but you're thinking about what you're saying, energy released in the phase transition.
Yep.
Where is this energy? Where was this energy before being released?
So this was in the false vacuum, right? Because in the false vacuum, you are here.
Okay.
The true vacuum, you are here. All of this energy is going out. And then it is a matter of how now this energy that is released, how this will turn into radiation, the heating. We didn't think about, like, there are some arguments, you have to be careful. We just assume that everything happens instantaneously. So your phase transition completes, and then all of this energy released, then it translates into radiation, usual radiation, and then you enter hot Big Bang.
Usual radiation, you mean photons?
Yeah. There are ways to do it, and especially when you are in this quintessential inflation context, it's very easy to produce only a little bit of radiation without having any weird couplings between the fields. You produce only a little bit, and then because of how the field behaves, the radiation will take over, and you will get usual hot Big Bang with no problems.
Okay, and what about gravitational wave emission? This is also part of the measurement.
So there is some, yes. So there is a fraction that is the gravitational waves there. Yeah, and this is also has to do with how strong the phase transition is. So yeah, some of the energy is going into gravitational waves, the rest is going into radiation. So second very important parameter in gravitational wave studies is this inverse duration. So how fast the phase transition happens. So this is inverse. So smaller means slower, right? And larger beta means faster. So same plot, you scan over them, and you need beta to be as small as possible, right? So you have to go larger sigmas in the same way as before. Now lambda here is more problematic, but we don't have to worry about too much. There are again some bounds here, so your phase transition has to happen fast enough. It completes before the background changes a lot, so you assume approximately constant Hubble rate. These are technicalities, we don't have to worry about them too much, and just to show you that the ideas that come into place. And it's coming back now to just refresh what is going on. So we saw this before. So the bubbles will collide and we get these gravitational waves produced there. And it's now by now a well-known prescription. There are all these LISA reviews and everything about how to calculate this. So gravitational wave spectra are characterized by two variables: peak frequency. So where is the height of your frequency in your spectra plots, and what is the amplitude there? So all of them now in this scenario, you have some variables that I talked about on the, so for example, for the amplitude, naturally how strong the transition is will affect your amplitude, right? Now the scale of the Hubble rate compared to the radiation domination also affects. You have here the equation of state parameter, how fast the transition happens. You have a spectral shape. This is just a numerical function. Temperature of radiation, right? Of radiation domination. So this is the prescription, and then whatever model you have, essentially you have to compute like all of the previous stuff that I'm talking about. You can disregard them. You take whatever model you want. You calculate this for your own model. You plug them in, and you get some spectra. This is the prescription. This is the comment I made before about this instantaneous thermalization. So we don't really. This is just to say that we're not doing reheating properly. We just assume that it happens as it should, just for the sake of simplicity. So your guy has already became standard model. You don't have any weird couplings. You don't have to worry about it too much. Yeah.
What is alpha?
Which one?
Alpha.
This alpha?
Yes.
Strength of phase transition. Yes. Energy release. Yeah. So the larger it is, the higher the amplitude. Yeah. So these are more interesting than the previous slides. So now to see what the spectra look like. So as I told, amplitude here, and this is the frequency. Like the two quantities you need to calculate: peak frequency, where your signal peaks, and then the overall amplitude, how it looks like. So here I've just written the previous expressions in a kind of more simplified form in this regime. We don't have to worry about it. It's just to see where all the variables are coming into place. So let's look at the solid line. So that means that now the scale of inflation is 10 to the 12. The usual high scale inflationary models that you have that are typical. Also for quintessential inflation, you can be around this scale, maybe 10 to the 8, not lower than that. This is the typical prescription. And you see now for all of these curves of varying strengths, you are way higher than the detector sensitivities. So it's not very promising. If we only have these detectors, then that means that this mechanism you wouldn't know if it existed or not. you have to go much lower in the scale, so around 10 to minus 8, in order for the signal to fall in within the windows. And the different curves just show you that the more the stronger the transition is, the higher the amplitude. This is what it is, right? What we were saying before. There is some tilt here that you see is not perfectly symmetric. This has to do with this extended period of kination. It's a technicality. You don't have to worry about it. It's just to show you this. So also this shape here, it works kind of as a smoking gun. If you see a signal like this that's not perfectly symmetric, one way to explain it is that you say you have extended period of kination in your early universe. And coming back to the very early slides, so because all of this propagate unhindered throughout your universe, so by looking at this, you can say something about the early universe that is going through CMB through everything, right? This is the importance of this type of studies. Okay, so for this plot, we just put a constant beta star number here just to play and show you the strength. You can do the reverse, right? You can assume a constant value of alpha and play with beta. So you see the same. Like at the high scale models, we are at the very high frequencies. You have to go very low in order to fall into the window. And now you see that the lower you go in beta, you increase your signal. Like the slower the transition is, so the bubbles grow and they become bigger. That's when you have a stronger gravitational wave signal. This is the idea. Okay, and then
So, but,
yep.
so which age infinity should we expect?
18, the scale of so that has to do now because we haven't specified the inflationary model. Now it has to do with what inflationary model you want to have. So in this case, like if you have this signal, that doesn't mean really anything. It means that you wouldn't know if you only have this low frequency detectors, right? There is a way, I have some slide afterwards. So when you are fine tuning your model, you can kind of massage it to go towards here, but then you are fine tuning, which is not illegal, but is not, you know, as appetizing. So you are fine tuning. You can try to make it there, but this is typical in this kind of primordial gravitational waves that you most of the times, because of the high scales of inflation, most of the times you have high frequency gravitational waves from these mechanisms. And this is a kind of common problem in this kind of early universe community from this type of mechanisms. Now in the phase transition community, because usually they deal with thermal phase transitions, so everything happens after radiation termination, the scale is much lower and you can get the signals to fall where you want them. But because in these kind of cold transitions before radiation, you usually have this problem. And I've seen people coming up with different ideas about your gravity or your inflationary. So some people have done this kind of hyperkination, so you get like some signals that are growing and then down into plateau and something like this. So there are ways of making them, you know, fancy, and you can get information out of them. But this is most of the time this is kind of a generic feature, unfortunately, for these early time phase transitions. Okay, so this is just to show you, like, besides the approximation, when you actually do the numerical calculations, you get the same picture, but now it's not as easy to show from before. But essentially, you see the same, right? The difference between scale and how your signal is affected from this kind of collective variable. So this is the idea. Now, if you want to just play this kind of fine tuning that I talked to you before, there is one aspect that you have to worry about is this kind of time integrated equation of state parameter that it has to do with when your phase transition happens and when it completes and everything. So it's not one just set it to one or whatever. You have this again, this kind of model dependent hints that I showed you before. So your sigma has to be somewhere around here, your lambda should be somewhere around there. But in order to have strong transitions, this should be as high as possible, this should be as low as possible. These are just
5 minutes.
sure. Yes, I'm finished. So these are just hint that you get about where to look in your parameter space. And here I'm just showing you some spectra. This is very rough, so it might be wrong that this is what it means. So if you play the game of looking at the specific radii sizes, so your critical radius is the one that when your radius is formed. So if the gravitational waves were generated here, so you form the bubbles and immediately generate gravitational waves, it would be of this amplitude. If they grow, and it's the typical approximation for percolation, then you get a signal like this. So you can, for certain parameters, which you don't have to worry about them here, you can try to make it go towards the right way to make it observable. But then you really have to fine tune here, and these are just some collection, but you can play around. Now this has to do with when your heating happens, different scales. It really comes down to fine tuning.
Can I ask one thing?
Sure.
So, for some reason, you stop right when we do the detect.
Yeah.
Why don't you, since you are just playing with numbers,
Yeah.
Is there any region of perimeter, the perimeter space that allows you to move to legal region? In the sense that imagine that light would detect some gravitational waves, and instead of doing this, you observe some gravitational waves and then do the opposite, trying to find what are the parameters that allow you to get this.
So there is the problem here. We don't show it because it would make the plot too big. But there is a horizontal bound at some point beyond which, if you produce more gravitational waves, it would affect your BBN.
Okay.
Your BBN would be messed up.
Okay.
And that means that now you're trying to push this more to the left, your peak will mess up your BBN. And when I was playing with the parameters, every time I tried little by little to change the parameters and make it go to the left, it would either mess up BBN or it would very dubiously come now down and avoid my parameter space for some reason.
This is suspicious.
This is very suspicious. So this is 50-50, me being a bad coder and my laptop, not being cooperative.
I apologize, but I disagree.
Yes. But that's why, these are very preliminary.
I mean, it's just there.
Yeah. The BBN is always there. Like this, I check every time you mess it up. Yeah. And this is the typical problem also when you have this kind of kination papers, because this give you more amplified gravitational waves. The problem with kination is that you mess BBN. So you have to have some mechanism to take care of that. So either the duration of kination has to be so that you don't mess BBN, or you have to have something else.
Okay. In BBN, there are also questions. So what is the main parameter from BBN that you do not want to destroy?
I think it has to do with the energy density. I think the energy density from the gravitational waves, if it's above a threshold, then you induce that in there and you mess up the usual hot Big Bang. I think this is the yeah. Okay, I think I should finish, right? So I have the last slide here. With just kind of overviewing what we did. So again, it's a very illustrative mechanism. We know that's why there are a lot of approximations and we're not super rigorous about every step. The whole idea is that to make this kind of proof of concept mechanism of generating gravitational waves that hopefully would be observable from curvature-induced phase transitions, not thermal, contrasting to the rest of the community, right? And the heart of the mechanism is this kind of dynamic mass thermal, the curvature. So if you specify the potential as we did, then you get some parameter space that you can look at and be promising. So for the mass, I didn't mention this. This is just kind of a summary of the paper. So for the mass, we want something that is always, of course, subdominant to the other term. For psi, there are some arguments about some minimum values so that you don't mess up some features of the potential. You have some sense of where to look for cubic and quartic. Unfortunately, we see that the spectra are, compared to the detector sensitivities, are not strong enough unless you are at the somehow the electroweak scale, so very low scale for inflation, which is really not physical. So obviously, one of the points is that we really need to be careful about treating reheating, because we did it in a kind of hand waving way. and this scale plays a role in the gravitational wave spectra. And then there is a matter of what kind of potential you can put there. So this was kind of an illustrative purpose. Right now in Porto, we are looking into whether you could use a Higgs portal dark matter scalar field to plug in there to act as this BSM and then have the curvature induce the phase transition and get some gravitational waves. This is very preliminary work. And of course now, if you want to look at the very standard oscillatory stationary potential, then you have multiple phase transitions, and that could also give you some non-trivial signature. So this would be kind of the ideas to go forward. But I think it has been talking for a long time. So thank you very much for listening, and I'm very happy to take more questions.
Well, the time was to leave some time for questions, so if there's any, please.
So I would like to ask about one clarification about the spectra.
Sure.
So these spectra, are these for single collision events or are they kind of the background?
Background is stochastic.
Yeah.
Stochastic. So this prescription is for this kind of. So this prescription is for percolation. So a lot of bubbles they collide. You assume that the phase transition completes, blah blah blah, and you get this stochastic background. It's not a single event.
As you have a background of gravity waves, you should have a background of scalar waves.
I don't know. We didn't look into that.
Mathematically speaking, they are there.
Yeah.
So you know,
I would assume they would be probably suppressed. I would assume, but I don't know. Do you know that? No. We didn't look into it.
Sorry, what is a scalar wave?
the wave traveling in the star field of the net.
Ah, okay.
Yeah.
I don't know what
I don't
perturbation is there.
I don't mean perturbation, a scalar perturbation of the net. I mean perturbation of all the star field.
Ah, okay.
I think on the assumption that everything goes as you want them to go, and then the phase transition completes, so your scalar field is here. So then probably the perturbation is small enough that you don't have scalar waves. So everything is kind of localized here. But now I remember there were some discussion I had with Javi about how localized is the field because it's quantum. So there were some things there. Now it's like more than 1 year ago we talked about. So I don't remember specifics.
The thing is that half of the field is there, but the other half is in the minimum.
But when the transition completes, everything is here, right? So if you look at the bubble picture,
Yeah, this is what the coupling becomes same. When you have the coupling, actually, you can keep the star field stable in the
you can, of course, for certain values. Here the assumption is that at some point everything turns black.
Waves collapse. And
Yeah. This is the point. And that's when now the gravitational waves travel after everything is black. Then they travel, and this is what you detect. That's the stochastic background that you detect.
So during the phase transition, the equation of state holds true. And what about sound speed?
Oh, sound speed. I don't know. Equation of state. I think there is a function between. There is a correspondence between equation of state and sound speed, right? There is a consideration of how fast the phase transition happens. Then the sound speed, because these are happening in vacuum, like the bubbles, so you don't have any plasma or something to affect your speed. So
The sound speed is pressure incubation.
yeah. So I think typically in these cases, after the bubbles form, they accelerate, they reach a terminal velocity close to speed of light. Typically, I think. In this one, I think we didn't even take it into consideration, but I think this is the typical prescription for this early universe bubble dynamics. I think when you have plasma, is a different discussion because how the bubble wall interacts with the plasma, you will have a different bubble speed.
And so when the bubble collides, so
Mhm.
when primary black hole form at
Mhm.
the boundary.
There are mechanisms to do that, yeah. So Marek with his collaborators has papers on so you can do that. I think then you need, it's not as generic. You need your potential. you need to to make it so to create these over densities. So, for example, one mechanism that these guys did was that you have this kind of bubbles, and there you had the lower energy density from the false vacuum, and then the false vacuum in the middle that was surrounded by these kind of lower densities that collapsed into a primordial black hole. So this was a paper from Marek and Ville Vaskonen, and these guys maybe like half a year ago, something like this. So there are ways to make it, and I think this community now is really coming in hot.
And so actually my question is, so if we consider primary black hole
Mhm.
that might provide another frame.
Sure, with the population of
Why if you have too many primary black holes.
Yeah, exactly. Yeah. So the idea is that, so let's say this mechanism works. Let's assume. So you can play the primordial black hole game. You can play the dark matter. So if you want now this BSM to explain dark matter, you have extra constraints from there. So it's not a free for all whatever theory. So the idea was that let's study the mechanism, and the real questions start now. What can you do with these mechanisms? Can you explain dark matter, or can you do primordial black hole something to be more physical? This is the game.
And I wonder, so your omega GW is something like alpha times beta star over.
Yeah.
So which means these two parameters are degenerate. So if in the future we accept that, how no, how large is alpha and how large is beta?
These parameters, you mean?
Yeah.
Is a degenerate channel. So, but for the calculation of this, there is specific prescription which I didn't emphasize. I apologize. So actually, beta is this like minus time derivative of your action, and in this model you get like kind of an analytic expression that depends, as you see, on the couplings. So whatever you see is couplings. This delta, which is also couplings, and you have this scale of bubble nucleation. So they're not really degenerate, and this ratio between them is actually the important parameter. So they're not degenerate, but you can treat them as a single variable. So, but you can disentangle, because this depends on your particle physics model. The scale of where it happens is your cosmology, basically.
Time for a last question if someone is scheduled. Yes.
Talking about the generosity of the parameter. My question is about the generosity with all your 100,000 effects that are there in the universe.
So now when I'm talking with gravitational wave people, actually the problem is how to disentangle everything that theorists are suggesting, and it's not easy. And then now they have all of these workshops in I think in CERN. They had one like a couple of months ago, and they keep having them. Is how to really disentangle and understand all of these stochastic backgrounds, how to deal with systematics. Everyone seems to suggest mechanism of generating gravitational waves, but it's not trivial. And from what they say, there's a lot of work to be done there, and theorists are now running to suggest models, and they cannot keep up. But Lisa will take some time to go up in space, so hopefully by then we will have covered some ground. But yeah, things there is a from when I'm talking to these people, there seems to have been a gap between the communities when talking about this, but now it seems that is not getting bigger; it's getting smaller. I see that people are talking to each other, and they are looking into bridging the gap.
There might be something to learn from what people are doing in galaxy surveys.
Mhm.
People
Very
have a lot of galaxies and everything, but they don't take it for measuring power effects.
yeah, and I think
you have a lot of effects. So maybe
I think so.
together,
I think people that are now part of these workshops, but this don't know for sure, but they are coming from different backgrounds. So some people I've seen come from astrophysics, some people come from gravity. Galaxies specifically, I don't remember if I saw people, but I know for sure that even for the gravitational wave, stuff. People are coming from binaries, from neutron stars, from cosmology. So it's really, of course, because when you're gonna look, when LISA goes up, you're not gonna see this signal. Hopefully, you will see a mess here. And then the real issue is to try to disentangle this. If you don't see anything, then that's a problem. Then we're gonna get blamed for a lot of money wasted if you don't see anything. But let's stay optimistic. There's always gonna be another frontier. Optimistic way to end. Yeah.
Trying to find black matter.
Yeah, I know.
Don't feel.
Well, we ran out of time, so let's thank Andreas again.
Thank you.
If you enjoyed the video, like and subscribe.